Hello, everyone. My name is Yi-Peng, and I'd like to talk to you about our work that I've done with my collaborators at UCLA and at Princeton about using graphical models and also logical formulas as an abstraction to analyze and to simulate quantum circuits. It's an exciting time to do quantum computing research right now. For a long while, we've known of inspiring algorithms, and also now we have prototypes that allow us to try running some of those algorithms. With that landscape, it's now important to try to build out the software tools to simulate and also compile and analyze quantum circuits. In this work, we talk about a specific new set of logical abstractions, intermediate representations for quantum circuits. So here I have a quantum circuit. In our work, we turn the quantum circuits into graphical models, such as Bayesian networks that can capture both the ideal circuit behavior of quantum circuits and also the noisy, unreliable behavior of quantum circuits. And then we borrow inference techniques from classical AI that turn them into different types of intermediate representation, such as logical formulas, and also other types of data structures that allow for repeated simulation, repeated inference, and different types of analysis. So here I want to talk to you about one such stage of our transformations. So here I've taken a quantum circuit that has qubit states, quantum gates, and noisy channels. And I've turned it into a Bayesian network where the nodes of the graphical model represent different states in the quantum circuit. The edges between the nodes represent dependencies between the states. And then within each node, there is a table that can capture the semantics of unitary matrices and also capture semantics of things like noise channels. The next step here would then to take this new representation and follow steps that were inspired by inference techniques that take the graphical models and turn them into logical formulas. So here I'm showing how a Hadamard gate can become a logical formula that talks about the input states and output states of the Hadamard gate. And likewise for things like the CNOT gate. And with this representation as a logical formula, we can then use tools such as satisfiability solvers, logical minimizers to compile the circuits into things like this one. This is an arithmetic circuit. And the fascinating thing about this representation is you can plug into the arithmetic circuit different possibilities that you want to simulate in the quantum circuit and follow the operations dictated by the compiled representation. And from this, you can calculate the correct probability amplitudes for quantum circuits. And so our work has led to some key findings. So the first set of results is that this is correct. So we're able to use these logical representations, graphical models, and do correct simulation of a canonical set of quantum algorithms. And we can use our toolchain as a simulation backend for open source quantum platforms. Secondarily, the unique capability of our toolchain is that it's super useful for simulating some important algorithms that are the subject of near-term algorithms, specifically these types of algorithms called variational algorithms, where a quantum circuit has to be executed many times with the same topology, so the same circuit setup, but with different parameters. And our compiled representation is uniquely suited to this type of algorithm simulation. And so here we're demonstrating how our approach in the purple series here compares favorably against quantum circuit simulators based off of matrix vector multiplication and also off of compared to tensor network contraction. And I'm doing this simulation for a workload that is a typical variational algorithm workload, QAOA. So to sum up, this talk highlighted a new set of intermediate representations for quantum circuits and how that enables new types of queries. With that, I'd like to thank my collaborators. Thank you.